Good afternoon, sir.
Good afternoon, Yasin. How are you today?
How are you today?
Thanks. Yourself?
Good, very good.
What happened? Did you receive any new material from your professor?
Yeah, last time we did a little bit of influence metrics, but it was just a review. But we also did, let me make sure I'm not saying anything wrong. Done Curly, I think.
Yes, thank you.
And modal matrix and its orthogonality. That I really didn't understand a lot. And
so I will tell you, approximately we are done because the chapter, the Riley approach and the Holzer method, chapter 12, and
yeah, there's only Thursday. Thursday is our last class. So basically, from the midterm to now, we did the how is it called? The matrix method for solving the equations. We did the how is it called? Lagrange.
Right.
And then influence matrix.
Right.
And then we have Dunkerley and then Heuser.
And that's exactly.
Perfect. So it's all dealing with matrices.
Right.
I think in class he said he won't give any very tedious examples like we did last time. Right. So it's going to be mostly it's going to be 2 by 2 or maximum of 3 by 3.
Right. So I have to turn it down. Okay. So yes, maximum 2 by in the worst scenario you will receive 3 by 3, but I have never seen 3 by 3. Okay. Maybe 2 by 2. But I've always seen Lagrange in the exam, and also
that's for sure.
So okay, I have to share.
No problem.
I have to share. Okay, so. So in this session, we are trying to finish the influence matrix. In the last session, I have solved a couple of problems, and we were determined to solve 6.4, 5, and 17. We already finished with 6.4, and today we will go for 6.5. And for the 6.17, I will tell you, I will solve one diagonal stiffness and diagonal mass, which is very good for decoupling a system that has several degree of freedom system. As soon as you decouple, for example, imagine you have a 3 degree of system, and in each equation you will see x1, x2, they are coupled basically. You cannot solve it. You have to go for Kramer or other method. But if we use a technique that allows us to face with 3 independent uncoupled, just one, the first equation of motion is only based on x1, and the second equation of motion is only based on x2, and it helps us to make the last equation of motion is only based on x3. If we did that through diagonal approach, then we would be able to just simply look at each equation and solve it like the way we did for chapter 2 and 3. So rather, we basically, for the sake of simplicity, we transfer a couple of, for example, 3x3 system, 3D graph system, which is coupled. We change it to a 3 uncoupled, 1D graph system. So one system which has 3D graph freedom, we make it 3 single D graph freedom system, which each of them is very simple to solve. That's why we use diagonal stiffness and diagonal matrix on the basis of mode shapes. So it helps us just in a simpler way solve the equation and find x1, x2, x3. Otherwise, you have the Cramer rule and you could solve any coupled equation. So let me start 6.5. There's a system. What we already talked about this issue, but I saw in the final one problem from vibration measurement, but I'm not sure whether it was in the summer or not, but maybe summer is very, but just have a look to make sure you can handle vibration measurement problem. So theta 1. So we are dealing with a system which has 3D graph freedom, theta, it's a triple pendulum, theta 1. So deflection of each pendulum, there is a vertical movement x1, x2, which is our coordinate, and also these angles are theta. So 6.5 and 6. Determine the influence coefficient for the triple pendulum. And so determine the influence coefficient. So at first step, you have to determine the number of degree of freedom systems. So here n is 3. Therefore, A would be 3 by 3.
So influence coefficient, that means find A, right?
Exactly. Influence coefficient, exactly. So yeah, you're right. Let me write it as you mentioned. Influence, it's better to write. Influence coefficient.
So that means we apply a force to one of the degrees of freedom and we see the displacement in the other.
Exactly. You're right. Exactly. Influence coefficient matrix. Influence coefficient, or it means matrix A. You are right. Basically A is 3 by 3. So A1, 1, A2, 1, A3, 1, A1, 2, A2, 2, A3, 2. A1, 3, A1, 2, 3, 3, 3. So as I told you in the last session, we have to first go for first column, right?
Yep.
As you mentioned clearly, in order to find the first column, we have to apply a unit force. So just always go for simpler coordinate. You could either go for theta, but the main coordinate, it is better to be x, okay? But x and theta are related to each other, no problem. So let me focus on x, and you could relate x to theta. So For the first column, we apply a unit force at the first mass, and we will determine the of first mass, second mass, and the third mass. So I like to focus on horizontal displacement, okay? And then I will apply a unit force here. No external force at 2, no external force at 3. So what is x1, x2? In this case, x1 will be translated as A11. x2 will be translated as displacement at 2 when a unit force is at A. Displacement at mass 3 when there is a unit force at 1. So very simple, very simple. So if I plot the free body diagram for the first mass. So imagine there is a triple pendulum and only you displace the first mass to the right. As soon as you do it, we will face this system. Okay. So this is A11, this is A21, and this is A31. If you take a look at here, you could easily notice A11 would be equal to A21 and A31. Yeah. Like the system we had in the 3 masses I solved in the last session. So just simply you could go, if I focus on the first mass, there is a basically force T here. So let's call this angle as theta, okay? So T tension in the string, so there is a 3 mg. So suppose M1, M3, M2, M1. So there's a mg force, right? So there is a free body diagram of the first mass. First mass. M1 plus M2 plus M3 G. So there is a unit force to the right. So this angle is, so this should be theta, right? So therefore, if I project the T here, T cosine and T sine. So we apply a static deflection and there is only acceleration. According to the second Newton's law, T sine theta, theta 1 basically, is equal to F is equal to 1. On the other hand, T cosine theta 1 is equal to M1 plus M2 plus M3. And what we are doing now, basically, I am heading to find these lengths. So A11, if you take a look at the first triangle, is going to be equal to let me tell you in a simpler way. Yes, if you want to say something, yes, go ahead.
Oh no, I said it's equal to the length of the chord times theta 1.
Yes, L, yes, exactly. If L multiplied by cosine theta would be this, or alternatively you could say sine of theta is A11 over L, right?
Yeah.
Okay. So this is a main important step. This is the main important steps. The rest, this is the first step I should have written at first place. So A11 is L sine of theta 1. So how can I find theta 1? That's why I went for free body diagram. I was trying to find theta 1. So A11, which is my aim to find, is L sine of theta 1. So if you take a look at here, theta sine of theta 1 can be easily obtained. So A11 is L sine of theta 1 is 1 over T. So what is T? T can be easily obtained from this equation. So T is M1 plus M2 plus M3G. Why? Because theta is very small. Cosine theta is approximately 1. So therefore, A11 is going to be there should be T. Okay, A11. Okay, exactly. A is L over M1 plus M2 plus M3G. Okay, this is A11, which is equal to A11 is A21 is equal to A31. Why? Because as soon as we look at it, we could indirectly understand. So you could fill out the first column.
Sorry, can you come back to A11 is equal to L 1 over T?
Yes. Here.
Down, yeah. Yeah, just
Okay.
a little. A11 1 over T.
Okay. Hello, answer. Okay, I see your question. I see your question. So I will tell you again. Okay, Yasin, we take a look at the picture and we notice sine of theta 1 is A11 over L.
Yeah.
So we were supposed to find A11. So A11 is L sine of theta 1. So we are heading to find sine of theta 1. So as soon as we draw the free body diagram, so here in the y direction there is a mg force, and we project the t in the y axis t cosine theta 1, and from the horizontal coordinate we have f is equal to
1
t sine here, right? So so t,
oh yeah, then you just isolate the sine
right.
theta 1. Okay, sorry.
Yes, I should have written. I isolate sine of theta 1 as 1 over t here. So you could easily plug in here sine of theta 1 here. I isolate and plug in here. But now I don't have t. So for finding the t, I'll go for the second equation I solve here. Since theta 1 is very small, cosine theta 1 is 1. So t is equal to summation of the m multiplied by g. So, okay. It is better to fill out the matrix before going to solve the second column. So A11 is okay. So it is the same. So then you have to write on the basis of symmetry theorem, reciprocity theorem, A ij is equal to AJI. Therefore, I can easily say A12 is A21. I already obtained A21 and just plug in here. And also this one, A13 is A31. Plus M2 plus M3. Okay. Right. So for the second column, we have to basically apply just force at the second mass. So imagine we have here, okay. This should be like this. F2 is 1. There is no external force at 1. There is no force at 3. So let's call. So if you take it, so immediately you could draw a conclusion that these two is the same. So this is A1 due to unit force at 2. This is A22 displacement at 2 due to unit force at 2. Displacement at 3 due to unit force at 2. Immediately you could draw a conclusion that A22 is equal to A32 at first shot. So, however, for, let's call it theta 1, let's call it theta 2. Okay. How can I find, so I'm heading toward finding A22. This is my goal. I don't have A22. So A22 here, if you take a look at A22 is this length. Is this length, but this length is, if you take a look at, you will see that this is A12, right? So A22 basically, so, or you could say that let me call it like this. So sine of, so you tell me, Yasin, what is the sine of theta 2?
It's so it's
this length is L.
Okay, so it's L over the. Now I'm just trying to picture the the sign, but in the opposite way.
Okay.
So it's A22 over L.
A22 over L. So a little bit. So this length is A22 minus A. This is A22, right?
Oh yeah. So A22 minus A1.
Exactly. Exactly. Yeah. So therefore, sine of theta 2 is A22 minus A12. That's it. This is the important step you have to take in order to find A22. So if you manipulate and isolate A22, therefore A22 is going to be A12 plus A2 sine of theta 2, right? Sine of, so let me, I have to write it. A22 minus A12 is L sine of theta 2, therefore A22 is L sine of theta 2. Okay. So okay, sine of, okay, so we already obtained A12 because A12 is A21. A12 is A21, we already obtained. A21 is L1 over G M1 plus M2 plus M3. So we don't have the second term. So we have to find theta 2. So we have to again go for a free body diagram for the second mass in order to find theta 2. So the second mass, there is a force M2, unit force, there is mg, second mass plus third mass, try to pull down the mass 2. There is a T force, another T2, let's call it T2. And this is basically theta 2. So therefore, this is also theta 2. T cosine theta 2 T sine theta 2. Again, simply T cosine theta 2 is going to be M2 plus M3 at G. Therefore, T is going to be M2 plus M3G. Because theta is very small, cosine theta is small. So from one hand, we have this, and from on the another hand, T sine theta 2 is going to be 1. So as you mentioned, we have to isolate sine of theta 2. Why we isolate theta 2? Because we need sine of theta 2 here to find A22. So 1 over T2, just plug in T2 here. That's it. 1 over, so we already isolate sine theta 2, just plugging back here above. So let me write here, because better here. Okay. To recap, we go for A22 is A12 plus L2 over M2 plus M3. Something wrong happened here. Something wrong. Where is L2 here? Okay, L2 is here. Okay, L2 multiplied by sine theta 2. Sine theta 2 we already obtained. Isolate here. Okay. This is A12 L2 sine theta 2. This is how we obtain A22. As soon as you obtain A22, A32 is equal to A22 according to the figure. So you could easily just go and fill out the matrix. Okay. L2 over M2 plus M3 GE plus L1 M1 plus M2 plus M3 G. So this is also equal A32 is equal to A22. Why? Because figure shows us. Figure shows us here. A22 is equal to A32. So before starting for filling out the last column, it is better to go check the reciprocity theorem to see if you could fill out the matrix. So here, this one, this is A23. According to the reciprocity theorem, is equal to A32. A32 we already obtained. Just plug in here. And the last array is A33, which is very important. So this one, similarly, by similar approach, we could find. Okay. So the last column, okay, we put unit force at the last mass and we calculate the displacement at all masses, but it is not necessary to go to find the displacement at mass 1 or 2 because it's already filled out in the matrix. So I just apply a unit force at mass 3, F2 is 0, F1 is 0. I'm not interested to find A1, 3. I'm not interested to find A2, 3 because these are already filled out in the matrix. I'm only interested in finding these lengths, which is A33. But if you further, in order to find A33, you have to take advantage of trigonomic formulation. So this is theta 3. If you take a look at this length, this is A33 minus A23, geometrically point of view, because this is A23. So you could take advantage of sine of theta 3 because this length is L. Sine of theta 3 is the front side. The front side is A33 minus A23. The front side over the L. This is the approach you have to find A33. So you need to find sine of theta 3. In order to find sine theta 3, you need to draw a free body diagram for the third mass. There is only M3G, which is pulled on the third mass. There is a unit force to the right. And the tension in the strings, let's call it T3. This is theta, therefore this should be theta. if I project the t in the two direction, t cosine theta, t sine theta, so similarly, you could take advantage of the previous sections. So similarly, I could say, mg, m3g, t3 cosine theta 3 is m3g, t3 sine of theta 3 is 1, f3. So here t3 is obtained, m3g, because theta is very small, and therefore sine of theta 3 is 1 over, if you isolate sine of theta 3, it will be 1 over t3 if t3 is obtained as m3g. So as soon as you obtain sine of theta 3, you just plug in here. Sine of theta 3, a3 1 minus a. a3 3 minus a2 3 over L is equal to sine theta 1 over mtg. So take a look at here and just try to isolate a3 3.
Yeah, it's gonna be. I think it's gonna be L.
So you could do it like this: a3 into 2 steps. a2 is L over m3g. Therefore, a3 is a2 plus L over m3g. a2 is already obtained in the previous section.
Yep.
So just plug in and insert to the matrix. I don't do it because there is no space in my place.
Oh,
so
no, it's okay. I got it.
So if you have any question, Yasin, just let me know. Otherwise, we will go for next problem.
No, we can go for the next problem.
Okay, perfect. So 6.17 is another example for influence matrix. 6.7.
So now here it's not the decoupling. Decoupling, we need a diagonal matrix, right?
Yes, for the decoupling, we will take advantage of mode shape. We will find diagonalized mass, diagonalized stiffness,
yeah,
and then insert to the equation of motion, and we will decouple them and just take advantage of chapter 2 and 3 and independently solve each equation by the formula we had in the chapter 2 and 3. So,
but for the influence matrix, like the example that we did, the matrix is going to give us like for an applied force, we can calculate all the resultant that can happen in the system.
I don't understand your question.
So when we find the influence matrix,
okay,
the definition of that is when, so we did for 1 unit of force. That means with the influence matrix, that means if we apply any other force, we can get the result really easily, right?
No,
I'm trying to understand the definition of the influence matrix.
Influence matrix just for solving equation. You only need to, for any single degree of freedom is done. For multiple degree of freedom, you always have to like construct this matrix, okay?
Mm-hmm.
K X like this, whether we have F or not. So just second Newton of law or Euler formula, but in some cases, K is difficult, but we will take advantage of, we have another approach to find K. A inverse is K. So we will introduce you the influence matrix in order at the end of the day to find K. But in the exam, you're not supposed to do like this, but just simply you have to know how to obtain influence matrix. It is not necessary to change it to a stiffness and solve the equation of motion all the case. Just but the philosophy why we do that, to my understanding, is just
to find K.
To find K, right? And
I think even the teacher said in the exam, if I'm asking for stiffness matrix, I don't want you to use that A to the A inverse equal K. So he's like, really, you need to find the K matrix without.
He said in the class.
Yeah.
So from which approach do you have to find K? From the approach I did in the last session?
Exactly.
Okay, that's it. Yeah. So because the philosophy here is that if you have 10 masses, okay, 10 masses spring linearly. So if you want to do a free body diagram and second Newton of law for each mass, it becomes very lengthy. So
yeah,
but by using this method, you just take a look at and just by taking a look at, just fill out the matrix in just 1 minute. For the stiffness, it's very simple, right? Yeah. That's why we have to use yes. We are not do it in the exam A inverse. There is no inverse. If you ask for a stiffness, you have to go for a stiffness. If you are asked for A, you have to go for A. But in your paper, if you have some time, if you want to double check, you may go for this. But you have to directly go for A if you're asked for, and for K if you're asked for. You are not going to, if you're asked for A, you are not supposed to find K and then inverse it to go A. You have to go directly. Exactly, he's right. You have to do that. So be careful to read the questions. But in your paper, you could, paper, you could do it by yourself in order to make sure you have already obtained the, at least you have the final answer. You could go for how I could reach to this. That's it. So 6 point. I remember when I was undergraduate, we only learned how to find a stiffness. We just took a look at the system, just fill out the stiffness. That's it. Yeah, okay. So 5 mass and springs. You could easily fill out the spring. So okay. Six point 6 point. In this course, I will tell you some important problem at the end. Just okay. Just remind me if I forget. So 6.17. So determine the modal matrix P and the weighted modal matrix P for the system shown here. Show that P or P hat will diagonalize the stiffness matrix. 6.17. Okay. Okay. L/4 okay, L over 4 mass modal matrix P. Modal matrix, so in this system, you could just model it by a theta, C, and X of C. X, if this point is C, just pure translational movement and pure rotational. These are the two coordinates. And the modal matrix is just put the first mode and second mode here. It will be modal matrix 2 by 2. Since we have
2 degree of freedom.
Right, and you could remove this crochet. Just simply put the. Okay, I would like to derive equation of motion using influence matrix, and then I will inverse A in order to find K. So be careful if you want. So here it is your choice. You can go for, so you have to construct the modal matrix. All you have to do is just find natural frequency and then go for mode shape. So for doing that, you need to find equation of motion. So you could easily apply the second Newton of law and Euler formula, but I like to go for A because I want to solve another problem to make sure you become master at finding A. I will find A and then take inverse to find K, and then I insert it here. So A11, A21, A12, A22. So the first column so let's call A11 is the translational movement X of C, and A21 theta, corresponding theta for the. This is a static equilibrium position. I will displace the system from a static equilibrium position to this point. XC is A11. And I put it a rotational like this, a theta 21. So there's a unit force here. Okay, for rotation, in the next step, I will tell you for the rotation, there is no any force. You have to put momentum. That's why I wanted to solve it by using A influence matrix. Mm-hmm. In the previous influence matrix, we either had only theta or X. Here is a mix of coordinate, theta and X. So nothing will change, but we consider the A11. So we put unit force to the middle point of the beam and displace the system toward the second point, first point and second point, and there is a rotation. There would be a rotation. According, if you take a look at the system, there would be a rotation because the K is not evenly distanced from the center of gravity. There would be a rotation. Theta 21 can be translated as rotation at second coordinate due to unit force at first coordinate. So as soon as you pull down the beams, there would be two forces which opposes the motion. One is like this, and the other is this. This is the total deflection of the left spring, and this is the total deflection of the right spring. So the left spring force is K deformation. Deformation is A11 minus this length. This length is L, half L multiplied by A21. A21 is theta 2. A21 is theta 21. It's theta, basically, just theta. Just theta, and so we need to basically, in order to find A11, in the previous question, we took advantage of geometric formulation and second Newton of law at y and x direction. Here we have to do it again. So I need to find A11. I have to somehow use second Newton of law. In the y direction, I found three forces. One is F1 is 1, and there are two spring forces that oppose the motion. I have just found the total deformation. For the left spring, it just comes from this point to this point. So this deflection is just this length, which is A11 minus this length, which is half L multiplied by theta.
21.
Exactly, theta. Exactly. So just construct the second Newton of law. Summation of forces applied at y is mx double dot c. So in order to find A11, just temporarily forget acceleration, because statically just displace the system is 0. Therefore, if I consider positive direction toward downside, there are two negative force minus K A11 minus half L A21 minus K A11 plus L over 4 A21 plus 1 unit force is equal to 0. So here, similarly, a spring force, this length is A11 plus L over 4 multiplied by theta, which is A21. This length is L over 4. This is theta, and you could find this length. So the red is A11 plus L over 4 multiplied by A21. Total deflection at the right spring. So here you have to just isolate A11 from this equation. And if I isolate A11, you have to manipulate further. K A11 minus half L K A21 plus K A11 plus K L over 4 A21 is equal to 1. So you could further simplify this, and therefore you would reach to this equation. 2K A11 minus L over 4 K A21 is equal to 1. So how can I find A11? while I don't have A to 1. I don't have A to 1. I have to do some manipulation. So what is your opinion to find A to 1? We need another equation. What should we do? Because we have two.
Yeah, we should do the moment, sum of moments.
Exactly. We have to take advantage of Euler formula. So similarly for this configuration, just apply summation of momentum around point C. Center of gravity is J around point C theta double dot. There is no acceleration, just summation of momentum equal to 0. So you could say clockwise is positive. If I come back, you will see that the left spring will create counterclockwise. However, the right spring will create counterclockwise around this point.
Mm-hmm.
This is left spring, this is right spring. Counterclockwise, we already obtained the force. Force is deflection multiplied by K. This is a force for each right spring and left spring. We don't have the force, just multiply by the corresponding arm here and here. And then just calculate here. Minus the left spring, K A11 minus half L A21 multiplied by the related arm, which is half L minus counterclockwise K A11 plus L over 4 A21 multiplied by the corresponding arm is equal to 0. If you manipulate here and if you isolate A11, it should be equal to 5 over 4 L A21. So I have two equations, A11 5 over 4 L A21 and another equation here. Let's call it A, equation A, and equation 2. You could say from 1 and 2 A21 would be 4 over 9 KL and A11 would be 5 over 9K. So A11, A21, A12, A22. So we already obtained this. We obtained this one. These should be the same. Therefore, this is obtained. The only array is left is A22. So you have to similarly repeat the procedure for second column. For the second column, we rotate the system and see what is the deflection. So we apply a unit momentum. So this is a system at the rest. So as soon as you apply the A22, as soon as you apply theta, imagine there would be resultant displacement like this. Displacement at 1 due to rotation at 2. There is a unit, this is center of gravity, and there is a unit momentum. Again, we have the same scenario. There would be two spring force. This is deflection, and this is deflection for the right spring and left spring. The left spring force is K, again K. The deflection is A12 minus half L A22. A22 is theta. Theta 2. And here the right spring force is K, again K. The deflection is A12 plus L over 4 multiplied by A22. So similarly, you could find A22. So you have to only just apply for momentum formula because we only need one array, A22. So summation of momentum around point center of gravity, if positive is counterclockwise, is I C theta double dot. See, there is no any acceleration. We imagine that we apply a static momentum. So positive K A12 minus half L A22 multiplied by the related arm is half L minus K A12 plus L over 4 A22 multiplied by the related arm plus 1 unit momentum, plus 1 unit momentum in this case. If I isolate A22 would be 32 over 9 KL squared. Why? Because A12 is equal to A21. A21 is already obtained. And all you have to do is I just wanted to show you how to find influence matrix if we have complex coordinate A11. It was not necessary to do that because you were directly asked for diagonalize. To find diagonalized matrix, you have to only just find the equation of motion directly using second Newton's law or either Lagrange. But for here, it's easier for finding second Newton's law and Euler formula. But for this system that you have to take advantage of, for example, the interconnection load, reaction, and action force, it is easier to go for example, pendulum. You have to go for T, reaction, action force. This is become complex and it is better to go for Lagrange. But here, if you are supposed to find equation of motion, it is better to go for second Newton's law and momentum formula. But you have to make just directly find the stiffness and M. You will directly lead to equation of motion. Here I wanted to review just the influence matrix 4 over 9KL 32 9KL squared. So A inverse, therefore A inverse is 1 over determinant. 1 over determinant is 5 9K multiplied by 32 over 9K L squared minus 16 over 81K squared L squared adjoint. The first column is just, you have to remove these two, positive, negative, and then go. For each array, you have to do that. Positive 32 left here, 9KL squared minus 49KL minus 9KL plus 9K transpose, which would be 9K squared L squared 16 32 9KL squared 9KL minus 9KL 9K transpose. Therefore, K, which is A inverse, would be a stiffness matrix is 2K minus KL over 4 minus KL over 4, 5 over 16 KL squared. And then you have to construct the equation of motion in matrix format at the first step. X double dot theta double dot plus 2K minus KL over 4 minus KL over 4, 5 over 16 KL squared. X theta is going to be 0. So if you will use second Newton's law and Euler formula, you could have reached to this equation, second Newton's law and Euler formula directly, and just construct. It was very, very easier, just 1 minute. Second Newton's law and Euler formula. But I was trying to, one more time, try to find influence matrix. So here, from now, we could start finding the modal matrix P. For the modal P, you need to find mode shape. For the mode shape, you need to find the natural frequencies. For the natural frequency, you have to go for in K minus M omega squared determinant equal to 0. You have to assume sinusoidal equation. X double dot would be minus omega squared X, and just plug in and reach to this equation. So therefore, simply the first mode shape would be if I let lambda omega squared M over K, for the sake of simplicity, lambda 1 would be 1.644. Therefore, omega would be omega n, right? Lambda 2 is 4.106, and mode shape L theta over X is 2 minus lambda. The first and second mode would be 1.424 minus 8424. So as soon as you obtain the mode shape. So the first mode is 1, 4 divided by L. Okay, let me do it like here, sorry. Okay. The first mode, X and theta, if X is if X is 1, there would be positive rotation. The second mode, so here you have to just theta, because this is ratio of L theta over X, therefore X is L theta over 1.424, therefore X over theta is L over 1. You could say that, you could say X is L over 1.424 theta, and let's make it complex here. Let's simply X. Okay, X over theta. If here, if x1, therefore theta would be 1.424 over L. This is how you have to construct the first one. So make one of them 1 and try to find the other one. And similarly for the second one. So as soon as you obtain the mode shape, just easily construct the modal matrix. Modal matrix P. Just simply insert here 1 over 1.424 L, 1 minus 8.424 over L. So we have to, so in the proof is in the book, how we have to decouple. So we need to show that determine the modal matrix P. We already obtained modal matrix P. The weighted modal matrix P hat, the weighted modal matrix. Okay, the weighted modal show P or P hat will diagonalize the stiffness. So weighted modal matrix is just, you have to divide this chapter 6. I have to go from here. Chapter 6. Okay. Okay. Modal matrix diagonalized stiffness. Okay. 6.3. Validation. Okay. 6.17. Okay. Weighted modal.
I think we just have to divide by the mass. Right?
Exactly. Modal matrix P hat is square root of mass, square root of mass divided by square root of mass, right? I forget this. Let me take a look at shortly. Weighted modal is just reciprocity theorem. Weighted modal, just simply weighted modal. Okay. A stiffness solution. Okay, orthogonality here. Orthogonality. Okay, we can easily go for. Okay, instead of P orthonormal, we up just square root of M11. Exactly, square root of M. Square root of 2. Okay. Weighted modal matrix, just all you have to do is just divided. For example, if P is like this, A, B, C, D, you have to, okay, the first mode, the second mode, right? You have to divide 1 over square root of M. Okay, I see. Diagonalized mass, okay. I see. Okay. M11 divided by AC and 1 over M22, okay. BT. This is, so we know how to find modal matrix P. We are done with P. But in order to find weighted modal matrix P hat, we have to divide first column, which is the first mode shape, divided by diagonalized mass. Diagonalized mass. Correspondingly, the second column by 1 over square root of M22. M22 is diagonalized. So by taking so before obtaining weighted modal matrix, you have to find diagonalized stiffness and diagonalized mass. Okay, diagonalized stiffness. You have to make it diagonal. It means these should be numbered. These should be 0 and 0. Diagonal stiffness. So K11 basically K11 0 0 K22 K11 and K22 are diagonalized stiffness, and diagonalized mass M11 0 0 M22. So how can I find M11 M22 diagonalized stiffness? How can I find diagonalized stiffness and diagonalized mass? Simply, all you have to do is just very simple. Let's go for diagonalized stiffness. It is basically written in the question, show that modal matrix P can diagonalize a stiffness K. In order to, we know what is a stiffness. We already obtained. A stiffness is like this. We already obtained a stiffness. We already obtained 2K minus K over L4 minus K L4 5 16 KL, thanks to orthogonality property of mode shape. So you could go for, you could calculate the diagonalized stiffness. Diagonalized stiffness is like this. Let's call it K hat. Diagonalized stiffness is P transpose KP. So P transpose, P we already obtained. P is the modal matrix. Transpose, you have to take each row and make it column, right? So, yeah. Okay, you know, okay, let's go for it. 1.424 L 1 minus 8.424. This is P transpose multiplied by K. K is 2K minus KL4 minus KL4 5 6 KL squared. I remember now one question in the final. You have to decouple and just, there was an initial condition, you have to take care of the response. You have to take care of the response. So 1.424, I will find the question of 1/4 over L minus 8.424 L. So if you multiply this matrix, you could either multiply the second two or the first two, and then multiply by the third matrix, and then you will reach by diagonalized stiffness. 2838833. So diagonalize stiffness, and similarly you could go for diagonalized mass. P transpose MP. I don't have M. P. So you have to go. So similarly, you will obtain by M. You could multiply the 3, and you will reach to this one, M11 and 0, 0, M22. As soon as you obtain M11 and M22, then you could obtain the weighted model. Just divide by square root of M11, the first mode shape, and divide by square root of M22, the second mode shape. This is the weighted. This is the weighted matrix. So simply, the philosophy behind all these calculation is just this. Simply, I think you have learned in the class mx double dot plus kx is f. If you decouple it, you could simply, so at first you multiply by p, and then you multiply by p hat, and then the coordinate transformation. X is py. Okay, you have to do a coordinate transformation. X is py. P is modal matrix. If you plug in back here, and then you will reach mpy double dot plus kpy. This is how you have to decouple if you are asked for. F is not going to change, just simple transformation. And then you have to multiply from the left by P transpose. P transpose mpy hat plus P transpose kpy f. P transpose f. P transpose f So this is a diagonalized mass, right? Let's call it, this is my notation, m hat y double dot plus k hat y is going to be p transpose f. So it is diagonalized. You see, if you m like this, m11 0 0 m22, k11 would be k22 0. So there would be two uncoupled equation of motion. As soon as you find y1 and y2 from the chapter 3, force vibration, two simple singular degree of freedom system, as soon as you obtain y and y2, then just plugging back here, just a simple multiplication here, you will simply obtain x. However, if you were faced with a coupled problem which was difficult, you have to take advantage of Kramer or other approach. This is why, this is how we decouple and take advantage of. So M11, M22, right? This is written in the book. You have to read the book, page 182 and 181. It is written, decoupling force vibration equation. Everything is there. So if you have any question, just ask me.
I think just in this example, to find m, it's simply the, let me just check. I forgot what was the question.
The question, okay, I will read the question for you. The question simply asks for determine the modal matrix P. At first step, modal matrix P. For modal matrix, you need to have first mode and the second mode. So how can I have first mode and second mode? You have to use either Lagrange, second law of virtual world, any approach to find equation of motion. As soon as you find the equation of motion, you could go for obtaining natural frequency. As soon as you obtain the two natural frequencies, you take one row of the matrix equation of motion and just simply divide it, isolate x over theta or x1 over x2, and then plug in first natural frequency and the second natural frequency to find the first mode and the second mode. As soon as to find first mode and the second mode, just put near together and construct the modal matrix P.
Yeah.
This is the first part. And the second part, we were supposed to find the weighted modal matrix P hat. The weighted modal matrix P hat. For the P hat, you have to just multiply 1 over
square root of m.
Yes, the first column by 1 over m11 and the second column by 1 over square root of m22. So how can I find m11 and m22? M11 and m22 are diagonalized stiffness. And also at the second part of the question, it says show that P or P hat, it means the weighted modal matrix will diagonalize the stiffness matrix, which we show it like this. So basically you have, once you construct the equation of motion, you have M from equation of motion, you have K. And you have more natural frequencies and you have mode shape. And by having the mode shape, you could construct the P matrix.
Yeah.
And then you could diagonalize mass P transpose M, P and P transpose K. P, this is diagonalized mass, and this is diagonalized stiffness. We were just wanted to show that this matrix can diagonalize matrix M, and this can diagonalize matrix K. And why we did that? Because in the next part we will need this if we want to decouple it. And also P hat is not P transpose. It's just P hat is just P, just divided by M11 for the first column and square root of M22 for the second column. It becomes P hat. That's it. And
Perfect.
okay. So I will advise you have to go for them. Just make sure you will solve it by yourself. Chapter 6, 6.4, 6.5 we solve it. 6.17 we solved it. 6.19, 6.19, 6.19. Determine the modal metric speed. P hat, diagonalize a stiffness matrix, thereby decoupling the equation. You have to decouple it as I did now. 6.19, 6.11. I'm not, you have not learned in this session. 6.8, 6.9, 6.90, 6.8, a stiffness. So you have to take advantage of a basically being two-sided constraint. 2L, if there is a F, you could model it by a spring. KF. If you model by a spring, K would be 192 EI over 2L cube and for the building, and you could, for the building, this is the formula it will give to you, but for the building, for the two, you could say that this point has the same displacement, and you could show it by two springs rather than one spring. So the two parallel spring, K is K hat divided by 2K hat we obtain here. This is going to be 24 EI LQ. This is going to be 12, right? So for the buildings, you could go for 12 EI over LQ. Stiffness of a half of fixed beam, guided clamp, or you could go for guided in the textbook of materials, mechanics of material. There is a guided. This is the same guided clamp, welded. If guided clamp delta is PL cube 12 EI, or a stiffness, in other words, is 12 EI L cube. I just prove it in another way. So you could go for buildings. It's very simple. 6.8, 6.8. Go for both A and a stiffness. You could do it both of them directly. You can obtain.
Perfect.
6.8, 6.8. Normal as orthogonal. There was a problem. Very important. One, orthogonal mode. Orthogonal 6.19. 6.33 is very important. That is very, very important. 6.33. Very, very important. 6.33. 6.33. The normal mode of the double pendulum is given, if the law is very important, the normal mode is given for the double pendulum. First mode, 2 natural frequencies is given, 2 first mode is given. If the lower mass is given an impulse, you have not learned impulse, right? In this session, impulse.
Yeah.
You have learned impulse. Chapter 4.
Yeah.
I don't think so. Chapter 4,
we did. I think we started with chapter 6. So no, not yet.
No. You will not learn impulse. Rather than impulse, maybe 633. Maybe there is an initial condition. For example, x0 is 0, x dot 0 is 1. For example, it's not rather than impulse 6.3. You have to, as soon as you obtain you decouple it, you have to decouple it and okay. Q is okay. Once you decouple it, okay, it's just chapter. Once you decouple it, you will reach to the chapter chapter 2 and 3. Simple. M2Q dot 2 plus K1 Q1 plus K2 after decoupling. Q is just transformation of the divided, so you could easily solve it. The chapter for just decoupling equation. Q is like this. Q can be A sine of omega 1 t, the free vibration. Free vibration is the summation, the response is a summation of natural frequencies. Omega 1 is natural, B sine of omega 2, A sine of omega 1, first natural frequency 0.764 G over LT, B sine of 85 G over LT. Rather than impulse, imagine there is a force, excitation, sine of, this is force, this is free. You could either use free or force. And then you have to, theta 1 and theta 2, you have to find A and B. It's a very good problem. A1, theta 2, initial condition, take derivative, theta 1 dot theta dot 2. You have to find initial condition, A, B, everything. You have to find A and B. So, but you cannot solve this question in this semester because you have not passed chapter 4. Just imagine rather than impulse, there is a initial condition. You have to go for free vibration. If there is an external force, you have to go for force vibration. In a force vibration, maybe there is an initial condition. So transient response plus particular response for each coordinate, first coordinate and second coordinate. For each coordinate, you may find 4 constant, A1, A2, A3, A4, 2 constant, one for initial condition, displacement, and the velocity. Initial velocity, initial displacement for each coordinate. 2 coordinates, 4 unknown. You have to find 4 unknown. Is a 2 by 2. 6.38. 6.38. This is another problem. 6.38. These are very important. 38. 6.38. So I wanted to start chapter 12. So let me start chapter. There are only 2 problems, 12.2 and 12.23. I will solve it next Monday, and then we are done. I think there will be no question. Just bring me your questions. We will review in the next session. I'll try to finish in 1 hour, and the rest we will review if you have any question. So I don't have any other problem, I can tell you. So 6 point, okay, there are some here. Okay, 6.18, I told you, right? 6.18.
Yeah.
6.19, 6.18. 6.18. 19 again. Uncoupling. 33. 33 is 33 is very nice problem. So 33, 38. So let me check. 6.3. 6.3 is not 6.3. Yes, 6.3. 6.3, 6.5, we saw 6.8, 17, we saw it today. Okay, 6.17. I have the P. Okay, 6.17, we solve it today. 6.17, P transpose MP is going to be a small m, factor out, 1.1690006.91. And K we already obtained. Weighted modal matrix is weighted first mode and weighted second mode, where weighted first mode is 1 over square root of first and multiply by the first mode shape. We solved the first mode shape and 6.91 m multiply by the second mode shape we already obtained. So 6.24. 6.24. 6.24. There is a damper. There is a damper. Damper. I think you are not going to ask for the damper. I don't think so. So the eigenvalue model matrix and normalized matrix. I don't think so. You will ask for damper. But you could still decouple it. Even if we have a damper in our system, you could decouple even C, matrix C. You could decouple matrix C and you have to force vibration. In the chapter 3, you had force vibration with damping. You could either decouple C, matrix C, 6.24, 6.34, 6.34. By decoupling the equations, we have 3 uncoupled equations. Each equation represents a single degree of freedom system under step function. So you have not a stem, but imagine there is a force excitation initial condition. So we are done with chapter 6 today and try to solve some problem. We will start chapter 12 and we will try to finish next session our teaching. But if you have problem, I try to come next Wednesday.
Is it possible to do one example next Wednesday about Dunderley?
Dunkerley?
Yeah.
The 12, okay. Dunkerley, Riley is 12.2, Holzer is 12.23, Dunkerley.
Oh, okay.
Are you sure you have read the Dunkerley equation? Dunkerley decoupling, chapter 12. Sorry.
I think it's used. Oh, okay. So it's chapter 12. Okay.
Okay, there is a Riley method. 12.2 is the Riley, okay? And 12.23 is so your Professor Ahmed has taught you Dunkerley method?
Yeah.
Okay. I will solve one and I'll be right here. 12.2 is Riley, 12.23 is Holzer, and plus 1 for Dunkerley. Okay. Dunkerley, sure, no problem. We will take care of Dunkerley in another question. So in the next session, we will try to finish the whole material. So when is your exam?
18th.
18th. Okay. Okay, we will finish next session, or I can come next Wednesday to see if you have any problem.
Okay.
So have a great day, and
you too. Thank you very much.
You're welcome.
Thank you.
You're welcome.